So you see that the system matrix for thin lens, we got it as 1 minus p1 plus p2 0 1, right? So now let's try to use this system matrix for thin lens and try to establish a relationship between the image distance or the object distance, image distance, and the radius of curvature, right? So the radius of curvature here in this matrix is embedded in P1 and P2. Recall that power is N2 minus N1 by R, right? So the radius of curvature is embedded in this power. So we have the system matrix for thin lens. So let's apply it. So if I have a thin lens, let's say if I have a thin convex lens, then if I have an object, somehow there would be a translation here, right? There is a translation, and we know the system matrix S here, and again there is another translation here. So you go from object to image, right? So you have a translation 1 followed by the system matrix for thin lens followed by translation 2, right? So now if I call this distance as negative d1 and this distance as d2, we are calling it negative d1 because it is towards the left, right? We are going in, the light is going this way from this to this direction, and if I'm measuring d1 in the opposite direction, it's negative d1, right? But d2 is onto the right side of the lens. So we have there we have let's say we have the image distance at d2. So we have two translations and the system matrix in between. So if I start with a point like lambda 1 x1 to go to the image where it is lambda 2 x2, first I go through a translation. So here the translation would be 1 0, right? The distance of translation is going to be d1, negative d1, right? So negative d1 1. I'm considering that this part is air, so I'm taking the refractive index to be 1. Then I have the system matrix. The system matrix is simply the system matrix is the system matrix is excuse me for that, that was a problem with the computer. So we have the translation matrix. That's the first translation from O to point P, and so the next is the refraction or the system matrix here for the two refracting surfaces. So that would be 1 minus P1 plus P2 because we are looking at a thin lens. So the thickness is almost 0. So that's why we have it acting as if it's just one refracting surface. So that's the system matrix we derived in part 1 of this lecture. And then I have another translation here going from here to the image. That would be similar to this matrix, except the distance is positive d2 because it is to the right side, right? So now if I do this, then I would have lambda 2 x2 would be equal to 1 0 d2 1, and this would give me 1 times 1 is 1, right? And p1 plus p2 times d1. So I would have 1 minus p1 plus p2 d1, but minus times minus gives me plus, right? Then I would have here 1 times 0 is 0. Here it is 1, so I would simply have minus p1 plus p2. And then 0 times 1 is 0. 1 times minus d1 is minus d1. And 0 times 0 is 0. 1 times 1 is 1, right? And then I have to do one more multiplication. Bear with me here. So I have 1 times this, which is the same thing, 1 plus p1 plus p2 d1. Same thing here. I just get minus 1 p1 plus p2, right? And then here I would get d2 times 1 plus p1 plus p2 d1 minus p1, right? and I would get here minus P1 plus P2 D2 plus 1 times lambda 1 x1, right? So if I were to write x2 in terms of x1, right? If I were to write x2 in terms of x1, I would have x2 is this times lambda 1, right? So that would be d2 1 plus p1 plus p2 d1 minus p1, and this whole thing multiplies lambda 1 plus whatever this is multiplies x1. Whatever this is multiplies x1. So I would have plus minus p1 plus p2 d2 1 minus that, right, multiplying x1. But if I start from a point here, right, along the axis here, there the height is 0, right? The height here is 0, and if the height here is 0, you know from ray optics that it just goes straight through. So height here is also 0. So if I set x1 is equal to 0, then that implies x2 is equal to 0, because a ray along this just passes straight through the center, because the angle of incidence is 0 here, right? So you just go straight through that, right? And so then if x1 is equal to 0, right, and then x2 must be 0. That means if I set x1 is equal to 0, this term is anyway 0. But if I have to have x2 is equal to 0, then I must have this coefficient to be 0. So I must have d2 1 plus p1 plus p2 times d1 minus p1 is equal to 0, right? So if I expand that, I would have d2 plus, I would have d2, then I would have p1, I would have p1 plus p2 d2 times d1 minus p1 is equal to 0, right? Should this be, this should be d1 not p1, so this should also be d1. This should be d1 not p1, so this should be d1. That's, sorry for my handwriting. So then I'm going to take this relationship, I'm going to write it on the next slide again. So we got d2 plus p1 plus p2 d1 d2 minus d1 is equal to 0. This is the relationship I got. Let me pause here and apologize for my handwriting. It is very, I know that lambdas and x's, it's a little bit confusing, because sometimes when I'm writing too fast, x may look like lambda, and same thing happened on the previous slide. I myself got confused between d and p. I apologize for that. I try to correct myself as I'm teaching. I apologize for this bad handwriting, but I hope you will be able to see the physics in it, right, more than the symbols. So you should take this as an opportunity to write it yourself and make sure that what I am doing makes sense. Okay, thank you. So here we came up with this relationship now. So then if I do a little bit of manipulation, right? So if I do a little bit of manipulation by saying I have d2 minus d1, right, would be equal to negative of p1 plus p2 d1 d2, right? So this is d2 minus d1 is equal to negative of that, right? So then if I take the negative sign and d1 d2 and pull them over to the other side, I would have d2 minus d1, I got a negative sign from the other side, divided by d1 d2 is equal to p1 plus p2. or if I rewrite it, I would get minus d2 by d1 d2 plus d1 by d1 d2. So here d1 and d2 cancel out, d1 d1 cancel out, d2 d2 cancels out, or I can write this as 1 over d2 minus 1 over d1 is equal to p1 plus p2. Or in terms of image distance and object distance, d2 is the image distance, d1 is the object distance. So I could write it as 1 over v minus 1 over u is equal to p1 plus p2 is 1 over f, where f is the focal length of the lens. So focal length of the lens is equal to p1 plus p2. 1 over f is equal to p1 plus p2. This is the same relationship we derived using ray optics, where we were drawing rays. Here, instead of drawing rays, we were able to determine it without drawing rays by using the matrix method, right? So what we essentially did is we started with a thick lens. In a thick lens, we saw that, for example, here, if I have a thick lens of thickness t, this is what we did in the first part. There is, if a ray of light is coming here, if it hits the surface at point P, we have one refraction, that is the first refraction, and then we had a translation, right, that is the second one, and then we had another refraction here at point Q. So we took all these three matrices, multiplied them, and got a matrix, a system matrix. We got a system matrix for thick lens, and in this thick lens I set the thickness to 0, and from there I got the system matrix for thin lens. And once I got the system matrix for thin lens, I used that system matrix for thin lens. I took a thin lens, I have the system matrix for thin lens. Then if I have an object here, it goes here and it goes there, right? So I looked at the object and image distances, right? I started from these coordinates, lambda 1 x1, and these coordinates are lambda 2 x2. By using the system matrix, there is one translation here and another translation here, and in between we have the system matrix. So I multiplied those three matrices, and we know that a ray that is starting from this side here, this way, goes straight through the lens and ends up here. Using that, we set the coefficients to 0, and from there we came up with the relation of 1 over d2 minus 1 over d1 is equal to p1 plus p2, and we define this p1 plus p2 as 1 over f, or what we call as 1 over focal length, right? So you may be thinking that if we know how to do this ray optics, why do we need to bother too much about using this matrix method, right? So let's do a couple of examples so this becomes more clear how powerful the matrix method is. So let's do one example here. So consider a sphere of radius is equal to 20 centimeters, right? And its refractive index, the refractive index of the sphere is equal to 1.6, right? What we have to do is we have to find the position of the focal point, right? So now you have a sphere. Now instead of drawing the ray diagrams, now you can simply see how a ray would pass through say a glass sphere, right? So if I have a glass sphere, right, then for example if a ray is coming like this, there would be one refraction here. Let's call this point A. There would be one refraction at point A, and then there would be a translation within the sphere, right? And another refraction say at point B, and then it would go down, something like that. So so there is one refraction, the first refraction, then here we have translation, and then we have refraction again, right? So then we can write simply the matrix, so we can derive the system matrix, right? The system matrix would be, first I have a refraction, so for refraction I would have 1 times the power, right? So the power here is n2 minus n1 by radius of curvature. Here n1 is say 8 and this n is 1.6. So power of the sphere would be n2 minus n1 by r, or the first refracting surface. N2 is 1.6, n1 is 8. So 8 refractive index, we are taking it to be 1. So 1.6 minus 1 by 20. 20 centimeters is the radius of curvature, right? So then I would have here 1 negative p, right? 0 1, that is the first refraction. And then I have a transmission or a translation through the glass, and the translation matrix would be 1 0. Here it would be d over n1. D is the distance, so the distance between point A and point B is 40 centimeters, right? They're opposite, diagonally opposite, so that would be 40 divided by the refractive index, which is 1.6, right? And again here I have 1. So then I have refraction at the second surface at point B, so again it would be 1, right? Here now this refraction is a little different from the first refraction, in the sense that at point B you are going from glass to air, whereas at point A you are coming from air to glass. So now you would have your power, so power reverse the signs. Here your n2 is 1.6 at point A because you are entering glass. At point B your n2 is 1 because you are exiting glass. So this is at point A, and at point B you have you would have the other way around, right? You would have 1 minus 1.6 by 20, right? So you can write those same things, right? 1.6 minus 1 by 20, and here you would have 0 and 1. So this would give you the total system matrix, right? So if you were to plug in this into the system matrix, you would get what the system matrix is. But our goal here is to figure out what the focal length is, right? So the focal length is basically we can get it from the system matrix, right? Because in case of an image formation, you are going from you have first a translation, and then you go through the system matrix, and then you get you get the image. So now if I do the math for these three matrices, what I'm going to get in terms of numbers is the system matrix would look something like this. If I multiply those, I would get 0.25 minus 0.0375, 25, and 0.25. This would give me the system matrix for that glass sphere, right? So once you have the system matrix, you know that the system matrix is represented as B minus A, right? Minus D and C. And if you recall the system matrix that we derived for a thin lens, right? If you recall the system matrix we derived for a thin lens, we had 1 minus P1 plus P2, 0, 1, right? So in case of a thin lens, A was equal to P1 plus P2, and we saw that P1 plus P2 is nothing but 1 over focal length. In the last lecture, we have seen that A is equal to P1 plus P2, and so P1 plus P2 is nothing but 1 over focal length. So here A is 0.0375, right? So that would be equal to 1 over focal length. And so your focal length, this is centimeter inverse. We used all the units in centimeters. The radius of curvature was taken as 20 centimeters. So now if I input that as a is equal to 0.0375, right, then I would get the focal length to be equal to roughly 26.7 centimeters. So just by using the system matrix and comparing the system matrix that we have to say a case of thin lens, we were able to figure out that this element, this second element in the matrix, should be equal to P1 plus P2, but P1 plus P2 is like 1 over focal length. So this whatever this number is 1 over focal length. So you can figure out that focal length is 26.7 centimeters, right? So now let's say instead of just one lens, let us say we have two different lenses, right? So how would we deal with that, right? So if you have two different lenses, two different thin lenses, let's say something like this. We'll do this problem in a minute. So let's say I have a thin convex lens, and then after some distance, I have a thin concave lens, right? So how would I deal with a system of lenses, for example, two different lenses? I know that the system matrix for this would be 1 minus 1 over focal length of the first lens, right? 0, 1. Similarly, the system matrix for this would be 1 over 1 minus f2, 0, 1, right? This is, I'm calling this as lens 1, this is lens 2, right? So if you have not understood how this is 1 over f2, please go back and look again. When we did the thick lens and substituted thickness itself, t itself going to 0, we obtained a system matrix for thin lens, and from the thin lens matrix we are able to clearly see that the P1 plus P2, the addition of the powers for a thin lens, is almost equal to not almost equal to, is equal to 1 over focal length, right? So from there we are able to see that whatever the second element is 1 over focal length, or simply addition of powers, P1 plus P2. So here I have two lenses. So I have the system matrix for each lens. So now I can determine how a ray, say for example, if I have an object here, a ray from this object may go like this, right? And it may go here, right? And go through this convex lens and concave lens, and maybe an image would form somewhere here like that. So this is my object, this is my image. Now we would like to completely do this without having to draw the rays, right? So what we do see is that this is a translation. So you have one translation, then you have the system matrix, then you have another translation, right? And then you have another lens, right? So so we would like to see how these lenses would work. Here I drew that this is going this way because again I just would like to give you an idea of how this ray may be refracting or reflecting. So here we have the system matrix for lens 1, here we have system matrix for lens 2, in between I have another translation. So let's see how we can handle two different lenses. So the system matrix for this entire system would be, the first I would have refraction, right? So first I would have refraction by the first lens. First I would have refraction by the first lens. Then I have a translation in between. If I call the distance between these two as d, right? Then I would have the translation matrix as 1, 0, d1. I'm assuming that the medium in between is 8, so I'm writing refractive index of that medium as 1. And then I have another refraction or another lens here for which the matrix is 1 over f2, 0, 1. So please note here, these things that are the system matrix for this thin lens is not just simple refraction. We derived this system matrix of thin lens. So we are using that system matrix itself to derive another matrix for a system of lenses, right? So this is a system of lenses. So for a system of lenses, for a system of two lenses, this is what the matrix would be. So if I were to do the multiplication, so I have the first lens 1 1 minus f1 0 1. Then the second matrix is 1 0 d1, and the third matrix is 1 1 minus f2 0 1. So if I do the multiplication, then I would have the first matrix remain the same, and the second matrix would give me 1 times 1 is 1, 0 times 0 is 0, so I have 1, and then here I have 1 minus f1, and then I have d times 1 is d, and then I have minus d over f1 plus 1, right? If I multiply it further, I would get 1 times 1 is 1, right? And I have 1 minus d over f2, right? And here I would get 1 minus f1, then I would get minus 1 over f2 times 1 minus d over f1, right? And here I would get 0 plus d, so I simply have d, and I would get again 1 minus d over f1. So if I were to simplify it further, I get the system matrix as 1 minus d over f2. This is entirely one term. Then here I have minus of 1 over f1 plus 1 over f2, that is 1 over f2 times 1. Here I would get minus times minus is plus. If I pull out a net negative as the common, minus times minus is plus. If I pull out a net negative common, I would get minus d by f1 f2. Then here I have d, and here I have minus 1 over df1, right? So from here, basically we can see what would be the focal length of the net system, that is the system of two lenses. Recall that this term, overall term, right, is 1 over focal length, as we have seen in the case of one thin lens. So the net focal length of the system here, system of lenses, would be 1 over f1 plus 1 over f2 minus d by f1 f2. It was so simple to derive, it hardly took any time to come up with this. Just by using the matrix method, we were able to very quickly come up with what would be this, right? So now let's try to do a simple example, right? For example, if I have two lenses, one convex and one concave lens, right? So I am given that I have a convex lens and a concave lens together, right? So let's say the convex lens has a focal length of plus 15 centimeters. A concave lens has a focal length of negative 20 centimeters, right? So that's the difference between the lenses. Recall the real images and virtual images and how we determine the focal lengths, right? So that's the sign convention at work here. So here we have the focal length of the concave lens as minus 20. So I will call this as f1, this as f2, and let's say these two things are separated by a distance of 27.7 centimeters. So the distance between these two is 27.5 centimeters, right? So if you have to now determine where the image is going to be, or what the net focal length is, then we can do that easily. So let's say this instead of 27.5, let's just round it up to 25, right? So then we can determine the net focal length. The net focal length is given by this formula. So we have net focal length as 1 over f1, that is 1 over 15, right, plus 1 over f2, that is minus 20. Then I have negative d over f1 f2. So let me write it here. 1 over f net is 1 over f1 plus 1 over f2 minus d by f1 f2. So d here is 25 centimeters, right? So d here is 25 centimeters. 25 divided by f1 f2. 15 times negative 20, so this becomes positive. So I have 15 times 20, right? So you can do the math, right? So I would have 1 over 15 minus 1 over 20 plus 25 by 15 times 20, right? So I can write that as net 15 times 20. I would have 20 minus 15 plus 25, right? So that would be 20 minus 15 is 5 plus 25 is 30. So I have 30, 15 by 20, 15 twos, 2 tens. That's 1 over 10. So the net focal length then for this system would be 10 centimeters, because 1 over f net is 1 over 10. So net focal length is 10 centimeters. So now if you are given that there is an object that is at a distance, say 100 centimeters from the first lens, that is 100 centimeters to the left of the object, right? So so we are given that u is 100 centimeters, negative 100 centimeters. You know that 1 over v minus 1 over u is 1 over f. So if I want to figure out where the image is going to be, 1 over v is going to be 1 over f plus 1 over u, right? So 1 over f is 1 over 10 plus 1 over 100, right? So that's going to be 100, right? So 10 plus 1, that's going to be 11 by 100, right? So that's going to be 1 over v. So v would be something like 100 over 11, roughly 10 centimeters, right? Roughly 10 point something centimeters. So that, so we figured out what should be where the image should be for a system of lenses without having to draw a single ray. So we have one convex lens of focal length 15 centimeters, another concave lens of focal length negative 20 centimeters. They are separated by a distance of 25 centimeters, and just by using matrices, we were able to figure out where the image should be, right? So this is how we can use matrices. So we have seen essentially the thing that I would recommend you to remember is the matrix for refraction. Refraction is 1 minus p01, where p is the power and p is defined as n2 minus n1 by radius of curvature, and you are going from a medium of n1 to into another medium of n2. That is the refraction here, right? That's the refraction matrix. So let me write this as refraction matrix Re, so that you don't get confused with radius of curvature. Then the translation matrix is 1, 0, d by n, 1. D is the distance between the 2 points between the 2 points of translation, and n is the refractive index of the material. So if you remember these two, you can derive a system matrix for any sort of lens, be it a thick lens, be it a thin lens, be it a system of lenses. And once you have the system matrix, you in general recall that system matrix is denoted as B minus A minus C and D, minus D and C. So that is in general how the system matrix is represented, and this A, as we have seen, is 1 over focal length. So once you have figured out for any given system, if you know the refraction and translation matrices, you can figure out the system matrix. Once you figure out the system matrix, once you know the second element here, you know that it is equal to 1 over f, so you know the focal length, and then you know the equations, right? 1 over v minus 1 over u is equal to 1 over f. So you use that. If you know the object distance, you can figure out where the image is. If you know the image distance, you can figure out where the object is, even for a system of lenses. Okay, so we'll stop here, and I will try to upload some example problems so that you can see these more clearly. Thank you.